All right, if you guys follow us outside of YouTube on different social media platforms, you've probably heard that my video production PC, which I use to make these videos and our online courses, ended up dying about 6 months ago. And unfortunately, it died the day we launched our second product or second physics course for you guys. Now, fortunately, that course ended up being successful and going really well. I was able to do a lot of the work I needed to do on my work laptop, but with my PC actually dying, that meant I had to research new parts, I had to build a new PC, configure it, and set it up with all my software, all my settings for getting all this work done. Now, as I was doing that, picking out different pieces, CPU, the graphics card, the RAM, so on, etc., for a new rig, and I started building it, I noticed that the heatsink I was using, if you don't know what a heatsink is, that's basically a huge metal construct with a lot of fins and a lot of surface area, which I'll talk about shortly, which is used to dissipate heat from a CPU and keep it cool. The heatsink I chose was massive, and as I was building, I was thinking about different heat transfer concepts I studied in college, and I thought, it'd be really cool to put out a video in which I talk about heat transfer from heat sinks and the fins in them that allows us to keep our rigs cool and to allow them to work efficiently. So the heat sink I was actually using, this is not a product placement. It is a pretty massive heat sink. It is the Legrand Macho RT, which is produced by Thermalright. I'm not going to take it outside of my PC. I can show you guys what it looks like inside of the PC while it's operating. This guy is massive. This is an air cooler, which is cooled via forced air. It's known as forced air convection. I'll go into that later. But this guy is pretty convoluted. There's a lot going on here. It's a work of art, a lot of engineering. So I was intrigued about the heat transfer properties, and that's what we're going to talk about in today's video. Okay, so before we jump into the actual heat transfer analysis and try to derive some kind of temperature distribution, what I want to do first is talk about a non-dimensional parameter we're going to make use of quite extensively throughout this analysis. So I want you guys to understand what it is. What is that? That is known as the Biot number. I know it's spelled sort of weird, B-I-O-T. What in the world does that mean? You do not pronounce it Biot. It's known as the Biot number. But in essence, this is a non-dimensional parameter used in a lot of heat transfer analyses. And it was named after the 18th century French physicist Jean-Baptiste Biot, who lived from 1774 to 1862. And in a nutshell, it's basically the ratio of two different heat transfer mechanisms, which I'll go into. The two heat transfer mechanisms are conductive heat transfer and convective heat transfer. So it's a way of showing the balance between the two, and depending upon what that Biot number is and how that ratio is scaled, you're going to get different phenomena arising in whatever you're analyzing, okay? So let's actually go over what conduction and convective heat transfer are. I'm going to assume you guys know little to nothing about heat transfer. So if you want to jump ahead to the good juicy parts, go ahead and do so. If you've heard about this before, if you've heard about the Biot number, go ahead and do so. But I think it would be a good idea to run through this with me just as a refresher if you've heard about it before. So the two different modes of heat transfer we're going to talk about here are conduction and convection. Conductive heat transfer usually takes place in solid materials, and the main mechanism of transferring energy throughout that body is done through the collision of particles and the movement of electrons in a body. So as we know, if we pick up any stationary object, maybe this marker here, this is a solid material. It doesn't look like anything is moving, but we do know that the energy that is inherent in this object causes the atoms that is composed of to vibrate very minimally, and those vibrations transfer heat throughout the object. So when you have conduction, those vibrations and the collision of the atoms tends to take this internal energy and dissipate it throughout that object. This is known as conduction. Very high conductive heat transfer tends to take place in a lot of metals. Copper, for example, nickel. These are commonly used in heat sinks. We'll find that this guy uses one of those metals. That's why it's made out of metal, to try and have a high conductive heat transfer throughout this entire device here. But that's the general mechanism at play here. And in terms of the mathematical description and the physics, Fourier, a scientist in the olden days, studied this kind of mechanism quite extensively, and he came up with a mathematical relation related to it, which is known as Fourier's law, which tells us how to determine and measure the heat transfer, or the change of energy per time, dq dt, and he defined that as a ratio related to a thermal conductivity, K, times the gradient of the temperature gradient coming out of the surface over the entire surface. So let's back up. Let's explain that with a picture. A little convoluted. So if we have two walls that are touching, or maybe we have two metal bars that are butted up against each other, and we want to figure out the heat transfer from this guy that is very hot to this guy that is very cold, or to make this make more sense, I'll use a red for hot and blue for cold. We want to know the heat transfer that's flowing through this surface area where they touch. Okay, so I've drawn up a picture here of those two different boundaries, and the way in which to determine the heat transfer Q is, the heat transfer is going to be the temperature difference across the surface area that it's flowing through. That's where this normal vector n comes into play. If it's going in a different direction, the heat transfer isn't going to be as much as it is if it's going straight through that surface area. But if we take this guy here and we use one dimension in the x direction, this can get a bit more simplified. So what we're going to use in this video, in this analysis mostly, is the following equation, where we take the heat transfer Q dot. It's basically this guy simplified down to there, new nomenclature. That is going to be proportional to this thermal conductivity, which is a physical property inherent in the material through which this is occurring. You can look that up in standard, I want to say dictionaries, but we have books that tabulate that information. And if you take that times the area it's flowing through, this surface area, and you take the derivative of the temperature across that boundary, you can get the heat transfer. So we can also approximate this by saying, okay, we can approximate that derivative. It's approximately the temperature difference between those two objects over the length over which it's flowing. And if we approximate it as such, we still can get reasonable answers, okay? So this is conductive heat transfer, just a brief overview, very quick, so you have some background on that. The other mechanism that is usually used for transmitting energy and transferring heat across different objects is convection, okay? So convection heat transfer has a lot to do with fluid flow. As the definition here says, this is heat transfer due to the bulk movement of molecules within a fluid which dissipate that energy. So what's going to happen is you can have two different forms of this. You can have forced convection or natural convection. In forced convection, which I have depicted here, we have some kind of fan that's blowing ambient air at a temperature T infinity. It's going to blow it over that object, and the air molecules are going to pick up heat as they roll over the object. Let's say some kind of plate. We'll assume that my arm is the plate. So the air is going to rush right by that bulk movement of the fluid. It's going to heat up here, and it's going to pull that energy out as it flows by. Okay? So you can think the higher the airflow rate, the greater the heat transfer in general. That's how it's going to work. Okay? Now, natural convection can also occur, and you can have both occurring at the same time. Natural convection is the fact that if you have some hot object here, natural convection states that the air molecules close to that surface are going to take that energy, right, because they're butted up against the surface, they're going to take that energy, it's going to get transferred to the air molecules, it's going to get less dense, and then it's going to rise due to that density gradient, if you will. So we know that more dense objects tend to sink. That's why ice in water tends to sink to the bottom. It's more dense. So the hotter something is, the lower the density is. So that low dense air on top of the surface of the plate, it's going to rise. That's going to create fluid flow, bulk movement of the particles, and that's going to pull away the energy that was once inside of this plate until we reach what is known as steady state, until there is no temperature differential, right? This tells us that the heat transfer mechanism is due to differences in temperature. Okay, so that is convective heat transfer, and as you can see in the video I showed you of the Legrand Macho RT, the heat sink, we see this fan attached to it. Okay, so the fan here is going to provide that bulk movement of molecules over these fins. So the fins are going to do conduction. They're going to spread out the heat within the mechanism, and then the air is going to try to pull that off and blow it away into the environment. That's how heat sinks tend to work. That's how we dissipate heat over our CPUs and keep them cool. Okay, and that's how I'm going to keep my CPU, which is a very big, beefy, hot CPU, an Intel Core i9-9900K, very hot CPU. That's how I keep it cool, using this big, huge heatsink, okay? So, we talked about conductive heat transfer. We got this equation here, Fourier's law. We talked about convective. We didn't come up with a mathematical description yet. So, the way in which we describe heat transfer through convection, it's also proportional based upon a parameter, the heat transfer coefficient H, but this is described by something known as Newton's law of cooling. Now, again, it's describing some proportionality idea. It's saying that the heat transfer is proportional to the temperature difference and the surface area, but we also have this, here's the proportionality constant, the heat transfer coefficient. Now, determining what that H is a very convoluted task. There's a lot of research done on this. There's a lot of stuff out there, a lot of literature. To determine this guy, we usually use a lot of empirical methods where we literally have experimental setups and we measure what the heat transfer is. We know these parameters that can allow us to approximate this guy. But there are a lot of different relations that come out of that, and it's quite a convoluted process to actually determine this. So throughout this lecture, I'm going to give you approximate values for that. We can reserve talking about H in future videos. If you're interested in it, drop a comment below. I'll get into that, let me know, and we can go to, I got a lot of books on that. We can talk about that. But in terms of this video, going back to the subject at hand, I said that the Biot number is trying to compare the heat transfer between these two different mechanisms. So we're going to use what I just discussed here to derive the Biot number and explain the significance it has in any kind of heat transfer analysis, any kind of thermal analysis, so on and so forth. So the way in which we derive the Biot number is by actually looking at something that is not related to heat directly at all. What is that? What am I talking about? So we can think of these physical processes here in terms of an electric circuit. And what is really beautiful in physics is the fact that regardless of the physical phenomena, sometimes we can come up with mathematical models that describe a broad range of physical phenomena. If we can come up with these mathematical models that encompass multiple physical phenomena, that sort of gives truth. It makes you feel like the universe intentionally made these physical phenomena arise in some way, or it's communicating to us in a really beautiful manner. So what's really cool about electric circuits is twofold. One, it's a very simple mathematical model, right? It's very linear. It's easy to work with. You know, V equals IR. And it's very useful in engineering for that reason. It's linearized, right? Engineers don't want to take a lot of convoluted math. They want to get answers very quickly and they want information that helps to guide their decisions very easily. The second thing is that if it can encompass multiple physical phenomena, that's really beautiful. Okay, so what I'm going to say is that if we take this model V equals IR, we can use the same exact model to describe heat transfer, what we just talked about here. What am I talking about? So let's review the electric circuit. The electric circuit states that if we have a potential V1 here and a potential V2 here, and we have the electricity or electrons flowing over some resistor, which is represented by this symbol here, right? We're going to have a current I that's flowing over it, and we can determine some resistance to that flow of the electrons going across this resistor here, okay? So what if I told you that if we took this, we can make an analogy with heat transfer? So the potential is what's really pushing the electrons across this guy. Well, what's pushing the energy from this guy to this guy? It's the temperature difference. It's this gradient. The gradient drives the heat transfer, okay? So we can see an analogy between the potential in electric circuits and temperature in heat transfer, and that's why I made this analogy here between T1 and V1 and V2 and T2. They're analogous. They have the same philosophical idea inherent in those concepts. So in electric circuits, when electrons flow due to that difference in potential, we say that there's some kind of current. The current is the flow of charge, okay? So in heat transfer, what we're talking about with that potential or that temperature gradient, we say that that creates heat transfer. The energy tends to move, and we measure the flow of that movement through this Q dot. So the heat transfer is sort of analogous to the current, and we can pair these two guys up here. Okay? Now, the only thing that is remaining is that the heat transfer may be great or it may be very small. And the amount of heat transfer is inherent in the properties of that material. If you use copper, it's going to be very high. If you use more insulating materials, such as plastic, it's going to be very low. So just like with thermal resistors, the resistor material and the size determines the flow rate of electrons over that actual object, okay? So we see that there's sort of this parallel where the material properties determine how the current, the flow of electrons, or the heat transfer, the flow of energy across an object. These parameters, the resistance, tends to determine how large or how small it is. So there's an analogy between the resistance of a circuit and a thermal resistance that we're going to call it a thermal resistance, which is the resistance of the material, okay? So we got an analogy in terms of the different variables. What about the mathematical linear relationship? So we know with electric circuits that we can say V is equal to IR. Can we get that kind of relationship here with heat transfer? Well, sure we can. We can just substitute out what we just got here. So a change in potential or a change in temperature is going to give us a flow of electrons or a flow of energy, Q dot, times the resistance. So with the electric circuit, we have the resistance of this resistor. In heat transfer, we have the resistance of the material, the resistance of the different particles and the collisions, how vibrant they are, how much energy they have, okay? So we can have this sort of mathematical similarity between the electric circuit and the thermal circuit, if you will, and we can use this to determine our Q dot, okay? So in a lot of engineering, the thermal analysis is reduced to determining this equivalent resistance, much like you would in electric circuits where you can have multiple resistors, parallel circuits, resistors in series, and you can reduce that down to one equivalent resistor. You can do the same exact thing in heat transfer analyses, where you might have heat transfer through this wall, you might have convective heat transfer, and maybe it goes down this path, the energy, or another path, and you can reduce it down to an equivalent resistance. That's what's done in a lot of engineering. We're going to take more of a physicsy approach where we take the equations of motion and derive the temperature distribution, but we'll get to that shortly. Coming back to the task at hand, the Biot number, if we can determine what this resistance is, we can form a ratio between these two heat transfers and determine whether it's more inclined to pour heat and energy through conduction or convection, and that gives us a lot of understanding in terms of how the heat is going to spread out in the material, how the actual physical phenomena, how it's going to transpire in front of us. So if we take these equations here for conduction and convection and put it into a nice format, we can say, okay, we approximated Fourier's law by saying that Q dot is equal to negative Ka, the thermal conductivity, times the exposed area, times delta T over delta X. If we move delta X, multiply by delta X, divide by Ka, we're going to have a little negative there. What we end up with is the same form here. We have delta T, sort of like the potential difference. We have Q dot, sort of like the current. And then this guy here, if we circle this bad boy, I'll use green. This guy, this gives us the thermal resistance due to conduction, okay? So this tells us that our conduction is going to be some length, delta L, over the thermal conductivity times times A, sorry about that. So we're able to get some kind of resistance that's equivalent to the electrical resistance. Sounds plausible, right? Let's do the same thing with convection. If we take Newton's law of cooling, HA Ts minus T infinity, where this guy, this is sort of like delta T, and we divide by 1 over HA, we can say delta T, again, the change of the potential or the change of temperature is equal to the Q dot, or the current, times this resistance here. This is the thermal resistance. So for convection, this guy we can pick off right here. It's in the same place. It's got to be the resistance. We can say from this that the convective resistance is just 1 over HA. Okay? So we're pretty much there. What we need to do now is take the resistance to heat transfer, and form some kind of ratio or relationship to come up with our Biot number, okay? So that's what we're going to do. I'm going to erase the board really quickly here, and then we're going to jump into that guy, okay? So after I erase this, I'm going to leave these guys right here, just so we have the resistance as reference. So the Biot number, let's go back to the definition. The Biot number is literally the ratio of conductive heat transfer to convective heat transfer. And in a nutshell, what that's saying is, it's trying to say how the temperature distribution within an object spreads out as time evolves. Okay? So if we take this can tell us the resistance to that actual mechanism. Does the heat want to go through conduction, or does it want to dissipate out of the object very quickly? So if we define it using that definition, we take the Biot number, it's going to be defined as the resistance to conduction over the resistance to convection, okay? Pretty simple relation. So if we plug in these guys down here, it's no big deal. So we have delta L for the resistance to conduction, delta L over Ka, over this guy, 1 over HAS. And I'll put an S here too, just to be consistent. The surface area. And so this guy just basically pops up, and we basically get something like delta L over KAS times HAS. We cancel this guy, and we find that the Biot number is defined as H delta L over K. That is the Biot number in a nutshell. Okay, so we just finished deriving the Biot number. What is its significance? Why should you care? And why is this so important and essential to the analysis of heat sinks and heat transfer in any kind of PC rig you've built? The first thing I want to make note of is this is a non-dimensional parameter, okay? And to prove that, we can look at the units for all these guys. Now, the heat transfer coefficient, that's usually given as watts, or that's going to be like joules per second, the energy per second, watts per meter squared, Kelvin. A length is going to be meter. And again, this is in the metric system. Well, not US, but you know what I mean, the metric system. Thermal conductivity is going to be watts per meter per Kelvin. So that's this guy. And if we take all the units, we see that that cancels. That cancels. This squared is going to cancel with that guy. This is going to cancel with that, because these guys pop up. The K is going to cancel with that. And in essence, what we get is this is unitless. So if it's unitless, that means that we can use this for anything we analyze, whether it's big, like my heatsink, or very small, like heat sinks in a laptop, for example. So we can use this one parameter to compare any kind of situation we're looking at, any kind of configuration. That's very useful for a lot of experiments we do. We do an experiment on one small thing, we can use it for a big thing. That's most commonly used in, let's say, for example, the aerospace industry. If you want to figure out airflow over like an airplane, it's freaking huge. You don't want to put this huge airplane in an air tunnel and do experiments. You can make a smaller model using dimensionless parameters and do experiments on that. If you derive dimensionless parameters, you can scale it all the way up to a huge airplane. The same exact thing applies with the Biot number. But the significance of the Biot number, as we explained, is it's a way of describing the resistance to conduction relative to the resistance of convection. And based upon what that parameter ends up being, this can tell us that either the temperature in a solid object will want to spread out, and that can give us very interesting situations, or, you know, we can have this disparity where the convection just wants to dissipate it, so we get that big, huge temperature differential near the surface. So in our case, why this is so important and why you should care is when this guy, this Biot number, becomes very small, or approximately 0, much less than 1, we get very interesting phenomena. Let's take a look at what happens here. When the Biot number is very small, that means that the resistance to convection is very high, and the resistance to conduction is very low. We can see that with this relationship here. If that is true, if this guy is very small and this guy is very high, very large, we get a small Biot number. In essence, what that is saying is a small Biot number has a high resistance to convection, but it has a very low resistance to conduction. So if you have a low resistance to conduction, if we derive what we got previously with the relationship to circuits, delta T is equal to Q dot R thermal. So if this guy is very small, what that means is you're going to have a small temperature differential. Let me just write it so you guys can understand, so you can look at it. We have delta T over Q dot is equal to RT. That means Q dot, the heat transfer due to conduction, is very high, and the temperature differential is very small throughout that material. What does that mean? What does that mean? That means that the heat tends to spread out in your object very, very quickly, but it can't really be released into the environment, okay? So a lot of interesting conditions arise because of that. And as I wrote here, in this scenario, the resistance to convection far outweighs the resistance to conduction. Heat is inclined to spread out in the solid. We get some universal temperature in that solid, but it struggles to escape or flow into the environment through convection. So one consequence of this is that if it's spreading out and the temperature differential is small, we can approximate the material as being isothermal. Let's break down that word, isothermal. Iso means equivalent, right? It means the same. And thermal, the equivalent or the same thermal, the same temperature. One temperature throughout a material. So if we can assert that a material is isothermal, that means that maybe there's only flow of heat in one direction. So if it's isothermal in, let's say, let me draw up a picture here. If we have like some kind of fin, hint, hint, and it's isothermal in, let's say, this direction here, well, we can eliminate that coordinate. We don't have to analyze it because we already know the temperature differential, the temperature distribution across it. But in this direction, in the x direction, let me put some axes here to help you guys out. We'll have x, y, standard coordinate system. In the x direction, you might still have a temperature differential, and that's where all the heat is going to flow. So because of this isothermal property, right, we may approximate the solid as being isothermal. This isothermal condition can allow us to ignore coordinates, to save us work, right? Usually we have x, y, and z in any kind of geometry. If we can eliminate z, that makes our life easier. If we can eliminate y too, it makes our life even easier, right? We have to solve less differential equations, invest less work to get results, to get answers to the problems we're trying to resolve, okay? So the final thing in terms of why you should care and why we're going to care in this video, in this analysis, is the fact that if you look at the heatsink here, you've seen pictures, the Lagrange-Macho RT, it's pretty convoluted, has a ton of geometry going on here, a lot of insane engineering. It's very complicated. This is not a simple problem. It's very complex. So if we can eliminate some of these coordinates, that can simplify the problem and make it more manageable. As I said here, geometry or engineering of heat sinks is very complex. So if we can ignore coordinates, the problem becomes much more manageable, feasible, and easier to solve, okay? So this is the Biot number. And if we could somehow show that the Biot number for our particular problem is very small, we can assert that the solid can be isothermal in certain dimensions. That can allow us to ignore coordinates, and that's going to simplify our problem, make our life easy, get us on track for solving the problem as efficiently and effectively as possible. That's the name of the game, baby. That's why we like the Biot number. That's why we're going to pay attention to it. And that's why it's going to be mentioned multiple times throughout this analysis. Okay? It's going to make it possible and manageable. Now, I talked about all this crap here. What we want to do, we want to take properties of this heat sink and try to figure out if we can prove that this is true so we can take advantage of all these conditions. Let's do that next. So let's go ahead and do just that. Let's approximate the Biot number for the situation at hand and see if we can take advantage of the benefits we just discovered to make our problem more manageable and easier to solve. Now, as I mentioned again, the heatsink we're using is the Lagrange-Macho RT by the company known as Thermalright. Now, fortunately, with a lot of engineering products, you can get a lot of technical specs, getting a lot of data, a lot of different parameters associated with the product on their company website, which is what we can do for this. Okay, so if we go to the company website for Thermalright, we can pull up a product sheet that gives us information regarding the geometry. We can get tech drawings, engineering drawings. We can get information regarding the material in this guy, the thermal conductivity for it. We can figure out what this fan is capable of doing, and using that information, we can get a very good approximation of the Biot number and see if we can use the assumptions we just discussed in the problem. Okay, so if we do that, we go to the website, we find the technical data sheet, we look at it and we review it, we find that it provides a lot of information regarding heat transfer, a lot of different parameters. What is very important is that we have a good summary of material properties. Now, according to the technical data sheet, this material, the base, is made out of copper. And this is very common in a lot of heat sinks because copper has a high thermal conductivity, okay? So that allows the temperature to spread out and to move quickly away from the base, away from the CPU that we're actually trying to cool. So if we take the material copper, we can look up in a tabulated book. I have a lot of books I can use. I did that. Copper is approximately 385 watts per meter Kelvin. That's the thermal conductivity. If you're doing this in real life, the appropriate way to do it is to get some thermocouples, a way for measuring the temperature, place it between two different points that we can measure. We can get the geometry, measure the geometry of some sample we're going to use, and actually calculate this firsthand to get a very accurate value. But the value should be pretty close to 385. Might be different by maybe plus or minus 5, who knows, depending upon the accuracy of the instruments we use. But that would be the appropriate way to actually do this analysis. And we would do the same thing for figuring out the H that we have to use in the Biot number calculation. Okay, next, what we can do, we can take the technical specs, we can take the engineering drawings, the geometry, and we can use that to figure out what this delta L, the differential, the position difference, the difference in length that this is flowing over, right? So we have to make sure that for the Biot number, the geometry we use is in the direction of heat flow. So if we take the fin again, what we're going to look at is we're going to assume heat is flowing in this direction, in perpendicular to this geometry. Okay, and the reason why it's going to become evident later in the video when we start doing the actual thermal analysis. But using this, we know that we need the fin thickness, which is thankfully provided in our documentation. Okay, so if we look at the thermal document, we see that these fins are quite thin, and that should be evident. Looking at our picture here, you see we have a ton of fins. That's sort of the goal of any kind of heat sink. We're trying to maximize the surface area through which the heat can dissipate out of. So that's why they're very thin. But we know it's very thin, so the technical data sheet gives us a fin thickness of 0.4 times 10 to the minus 3 meters. Very small. That jives well with our intuition. Makes sense. So we can take that. And the only thing that remains is to estimate probably the hardest part of this, which is the heat transfer coefficient for convection, the H term here, and that's done by analyzing the fluid flow properties. Now, as I mentioned previously, calculating the heat transfer coefficient is very complicated, very complex, and it involves a lot of work. I could make a few videos, maybe even an entire course just on convective heat transfer. I'm going to refrain from doing so because that would take up too much time. That's not the intent of this video. Instead, what we can do is we can take general relationships. We can use different sources for getting tables, so on and so forth. But what is very important to understand is that the flow of the fluid, the bulk movement, as I mentioned previously, determines the value of the heat transfer coefficient. The higher the movement, the more the volume flow rate, Q, which I have here, the higher the heat transfer coefficient is going to be. So if we look at the technical data sheet, what it gives us a value for the airflow of 16.9 to 73.6 cubic feet per minute. Okay, so that's CFM, cubic feet per minute. We would have to convert that back to this unit system with meters, the metric system. But when we do that, we can look at a table or maybe a plot somewhere that did all the work for us, and estimate what this heat transfer coefficient is going to be. So I did that offline. We're not going to go into that, but that gives us a heat transfer coefficient of approximately 50 watts per meter squared Kelvin, which is not a bad heat transfer coefficient, okay? This is what the fan attached to our heatsink is capable of doing, okay? So we got all these numbers, we got all these parameters, we can attain them from experiments. If we want very accurate numbers, what we need to do is just plug and chug, baby. Take these numbers, plug them in here, get a value. So if we do that, we take the Biot number. We know the Biot number is defined as H delta L over K, the thermal conductivity. And we can just plop these guys right in. So we get 50 watts per meter squared Kelvin times this guy, 0.4 times 10 to the minus third meter. And then we divide by the thermal conductivity. You can tell right now it's going to be a small number, right? And this guy's freaking huge. We get 385 watts per meter Kelvin. And if we cancel the units just to make sure it works out, Kelvin cancels here. This canceled that, and this guy canceled that. Indeed, we get a unitless value. This is the point at which you pull out your calculator, MATLAB, Mathematica, whatever you want to use. I did this offline. I'm not going to do this here. Maybe you can pull out an old school TI-83 back from your high school days. But at any rate, when we do this, we see that the Biot number is a pretty small number. We get approximately 5.19 times 10 to the minus 5, which is much less than 1. Okay? So we see here that we took all these different properties associated with the situation we're analyzing. We calculated the non-dimensional Biot number. It's much less than 1. It's very small. And so that insinuates that since it's very small, at least in the direction of the fin, that perpendicular direction, heat transfer is going to spread out very quickly due to conduction, but it's going to struggle to be dissipated through convection. In essence, convection is the bottleneck. That's generally what happens, especially with metals. It's easier to flow through metals than it is to dissipate through the air. That's going to be the bottleneck. We're going to get sort of an isothermal property in that fin, at least in the y direction. It's going to be different along the length of the fin. So that's going to allow us to say it's isothermal. We're going to be able to eliminate a coordinate that's going to simplify our lives. It's going to simplify your life. Less math for you. It's better. And then we can get to an answer for a problem, getting that temperature distribution and the heat transfer that's going through this heat sink very easily. So what did we discover in this video? In this video, we discovered that the Biot number is a way of measuring the way in which heat transfer is exhibited in any kind of object. Does it tend to go through conduction or convection? And it's a way of comparing the two such that we can figure out how temperature is going to be distributed throughout an object. If the Biot number is very small, that means it's going to be very high conduction in the object, but along its surface, the convection is going to be a bottleneck. It's going to struggle to dissipate that heat that sort of goes throughout the object. But as a result of that, we get isothermal properties. We can eliminate coordinates. It makes our life simpler, okay? So that's the Biot number. We calculate the Biot number. We're going to use this approximation pretty extensively throughout our analysis. Maybe 3 times throughout our analysis. It's quite a lot. It's going to help us a lot. Keep this in mind. I hope you enjoyed the video. Stay tuned for jumping into that analysis. We actually, derive that temperature distribution within our heat sink and get a better understanding, a better appreciation for what these devices are doing for keeping our PCs cool and allowing us to do the work that we need to do. Thanks for watching.